Hi everyone and welcome back to my channel. Today I want to talk about an amazing Udemy course that I published a couple of months ago about the 20 most common code smells and how to get rid of them. I truly believe that the course is a great way for you to become a better developer by learning how to identify and quickly address a couple of the most common bad practices when working with code. There are other very important topics that I cover in the course, including the solid principles, refactoring, and also design patterns, all that will help you write better, more efficient, and more maintainable code. Also, if you enjoy the content I produce and you want me to publish more often, purchasing the course is a great way to support the channel while also getting something back in return. And of course, there is a big discount for you here. The link is on the description, so make sure to check it out right now. Great, so I want to give a little taste about what the course is about. So I'm putting here a whole excerpt about the solid principles, the single responsibility open-closed principle, Liskov substitution principle, interface segregation principle, and the dependency inversion principle for you to enjoy and to see what the course is about and the type of content that I cover. That's it for today. The link with a big discount is on the description of the video. Enjoy the solid principles and I hope to see you in the course. Bye bye. In this video, we discussed the single responsibility principle. This is the first one, the letter S of the solid principles. And it says that an entity should have only one reason to change. In other words, it should encode one single part of the domain knowledge. It leads to code that is easier to maintain, it's easier to extend, and it's easier to understand. And if you violate this principle, you can quickly get into situations of high coupling between multiple responsibilities and code that is harder to maintain. Here is one example for us to understand this concept. Let's say that we have an order manager. So this order manager, thinking again in the example of the e-commerce store, it houses a couple of responsibilities. It has some code for the inventory management, it has some code for the shipment management, and it has some code for the invoice management. And as you may expect, these modules, they need to call each other. They need to get some functionality out of each other. However, because there is no abstraction between them, they are all within the same module, we start getting dependent on implementation details. So we are calling the direct methods of each of these different parts of our order manager. So when we are grouping everything under the same class, it's easy to introduce direct dependencies between the different responsibilities. And this can lead to cases where we are changing the inventory management, for example, and we need to directly change shipment and invoice management. And here we are working always with details. And we don't like to work, as we already discussed, we don't like to work with implementation details. A different approach which we can take to solve this problem is splitting this order manager into different entities, into different classes. Now we have an inventory manager, which is separated from the shipment management, which is also separated from the invoice management. And we expose clear interfaces, clear, stable interfaces. Then each of these individual modules, it implements these interfaces. The question is, what happens with these dependencies between the modules? Well, now the invoice manager cannot just go and directly call the inventory manager, because the inventory manager is hiding its implementation details behind a stable interface. So what happens is that the modules will start depending on the interfaces of the other modules. This gives us a great layer of abstraction and encapsulation here, because the interfaces, which are inherently more stable than the implementation details, they're going to be used by the other modules, and we are then free to actually manage and change the details of inventory manager as we please, and we don't need to worry that these implementation details or changes in these implementation details are actually going to break our other modules. The idea here, to summarize, is have a single reason to change, have a single responsibility per class, per entity, expose this responsibility via a stable public-facing interface, And whenever you have dependencies into other modules, make sure you are dependent on their interface and not on their implementation details. In this video, we will discuss the open-closed principle, the O of Solid. And it says that entities should be open for extension but closed for modification. In other words, we should be able to add functionality by writing new entities in code rather than having to modify existing code. How does that look in practice? Let's think of an example. Let's say that we have a data store, and this data store has two methods. It has one method to read from a file, and it has another method to save to a file. And we have to pass the path as an argument whenever calling these methods. Now, what happens if we want to, instead of managing data in files, we want to manage this data via HTTP endpoints? Well, one possibility would be for us to simply replace these methods, read from file and save to file, by read from HTTP and save to HTTP. Now, this is very cumbersome because any module that depends on this read from file and save to file will have to be updated to use the new method. So basically, by us simply changing the name here, we are introducing a breaking change. This is a change in our interface. It's a change in our public contract, which means that any other module that uses the data store will have to be updated. They will have to go into their code, they will have to fix the names of the methods, and they will lose the possibility of working with files. So we have modified our functionality, we have adjusted it to new requirements by modifying our existing code. And as you may expect, this is very nightmarish to maintain, because if tomorrow it's not HTTP, it's maybe back to files or to something else, we need to come back here and we need to change this code again. That is not desirable at all. So how do we tackle the problem? Well, the solution here is, as you may expect, for us to introduce a sensible abstraction on top of our data store. So instead of having methods read from file, read from HTTP, and so on and so forth, we have a stable interface. And this interface tells whoever is using our module, it tells, look, if you want to work with our data store, here are two methods. There is a method to read from somewhere, and there is a method to save to somewhere. We have this abstraction, and we can start adding functionality by creating modules, creating a file store module. And this file store module is going to implement this interface iDataStore, and it's going to provide the methods read and save. Now, if we want to then comply to the new requirement of using HTTP endpoints, we don't need to come to the file store module and change it. We don't need to touch the file store module at all. We can create a new module called the HTTP store module. And this module will also comply with the data store interface, and it will provide a read and a save method. The idea here is that we are adding functionality not by changing code that is already existing, but by adding new code. And an additional benefit of it is that any module that depends on this abstraction can quickly swap between file store and the HTTP store because they both comply with the abstraction. So any module that works with the iDataStore interface will automatically work with file store and with HTTP store. That refers back to what we discussed on the concept of polymorphism, and that's why polymorphism is so important. Let's talk about the Liskov substitution principle. That's the L of Solid. And the Liskov substitution principle, it simply says that if an object of type T is a subtype of another object of type S, so basically S is the superclass and T is the subclass, then any object of type S, the superclass, should be substitutable by objects of type T, the subclass, without breaking the application. That means, in simpler terms, because that doesn't sound very simple, that subclasses should not implement any behavior that contradicts or that restricts the intended behavior of their superclasses. Let's have a look at an example. A typical example from university is having an animal class, and this animal class has a method called the walk method. Now, if you stop and think for a second, not every animal walks, right? So a bird, it doesn't walk, it flies. I mean, maybe it can walk in some circumstances, but the default behavior of a bird is to fly. A fish doesn't walk, it swims, right? So a tendency that we have is to, well, birds are animals, so that's why the inheritance relationship here. But because they don't walk, what we do is we override the walk method of the animal superclass, and we throw an error. And this error here is simply contradicting the behavior of the animal superclass, because an error is not expected when calling the walk method. That means that I cannot take the animal superclass and simply substitute by any of its subclasses, because if I substitute by a subclass which is of type fish or which is of type bird, then my application will break whenever calling the walk method. Here, perhaps it is a moment for me to tell you that I hate inheritance and that I 99.99% of the time prefer composition. That's why I didn't mention inheritance in the foundational concepts. It is because it makes our lives as developers harder. So between inheritance and composition, always go for composition and stick to inheritance at very few cases. With that being said, how do we actually tackle this? Well, the walk method to begin with is not looking very good because we know that not all the animals walk. So our conceptualization of a superclass here is actually incorrect. That leads us to these problems of having to override the walk method and throwing errors in subclasses. So perhaps a different approach would be to simply rename the walk method and not expect all the animals to walk, but at least to move. I understand, I know that not every, I think there are some examples of animals that don't move, but then in this case, we could simply implement an empty method. We just do nothing instead of throwing an error. And then for animals which move in different ways than walking, we can implement the functionality here. So for bird, when the bird moves, it's going to simply fly away and the fish is going to swim away. So by redefining our superclass, we can actually derive the correct abstraction, derive the correct behavior of the superclass instead of incorrectly defining it and then having to implement code in the subclasses which is not really matching the expected behavior of the superclass. Let's talk about interface segregation principle. That's the I in solid. Interface segregation means that no code should depend on methods that it does not use. So if a certain class C implements an interface I, then that class should not have to provide empty implementations for methods it doesn't need. If this is the case, then it is recommended to split the large interfaces into smaller ones, as to allow the classes to implement only those methods that they really need. Let's think of an example. Let's say that a certain interface here, it houses some functionality and can think back to the inventory manager, the shipment manager, and the invoice manager. So a certain interface has methods for all of these three functionalities. Now, let's say that I want to implement the functionality of managing inventory. Well, because I have only one interface, then whatever object that I want to use to implement this functionality, it implements the whole interface, which means that it will implement the actual functionality for the inventory here, but it will also have to provide either empty methods or not implemented methods for the interface, the parts of the interface that it's not interested in. When this starts happening, it's a signal that we are actually incorrectly defining our interfaces. So instead of having a single interface with a lot of functionality in it, a better approach is to split the interface into three different interfaces. We already saw this setup earlier. Then, if I want to implement the inventory functionality, all I have to do is to implement the inventory interface. my class here doesn't become bigger than it has to, because it doesn't need to provide empty implementations for the methods it doesn't need. This is another very important principle which makes our lives as developers much easier. And also something that is a consequence of this, that it's perhaps a little bit harder to realize, is that in the case on the left, whenever I work with this interface, I am another module, okay? So I'm just another module using this interface. I actually expect whatever module I'm using that complies with this interface, I expect that the whole functionality is there, right? But if I'm providing empty methods to parts of the interface that I don't need, that means that other people using the module are going to have a tough time learning and keeping in mind that I don't provide parts of the functionality, that I provide only the blue functionality here. So this is another very, very bad consequence of not properly segregating, not properly separating our interfaces. We create this expectation on others that our modules provide the whole functionality represented by the interface, but this is not always the case. If we properly separate the interfaces, we know, or other people using our modules know, and they can rely on the fact that if they are seeing the methods exposed by the interface here, they can rely on the fact that we are properly implementing them on the modules that we are providing. This is another very important aspect of properly defining interfaces. Let's discuss the last of the solid principles, the dependency inversion principle. This is the D of solid. And it states that high-level modules should not depend on low-level modules. Instead, both should depend on abstractions. Additionally, abstractions should not depend on details. Instead, details should depend on abstractions. Let's go back to our example of our file store. And now let's say that we have a new class, a data display class, which depends on a concrete instance of file store. So it has a variable of type file store, which then holds a reference to a file store object. And this file store object has the methods read from file and save to file. Here, once again, if I want to swap out a file store for an HTTP store, then I actually need to revisit all the code in data display that calls the methods read from file and save to file. And I need to update these methods to be the read from HTTP and save to HTTP. And basically, it's hard to maintain. Here you can see that the interface, that the methods of file store are depending on details, right? It depends on the file here. And if I switch to HTTP, it then depends on HTTP. And this is a detail which makes it harder for us to change our code. So what the dependency inversion principle instructs us to do is that instead of having this direct dependency of high-level modules into lower-level modules, we define an interface. And again, that's the same interface, the data store interface, and it has methods which do not depend on abstractions. The read method and the save method, you can see here that by their name, they are not dependent on whether this is coming from a file or whether this is coming from an HTTP endpoint. They are generic methods, and they are simply abstractions. And what we do is that our data display class now has a variable which is of the type of the interface, and it holds, or it doesn't hold an interface here, but it simply requires any concrete instance that complies to that interface. Now, the lower level modules are then going to implement that interface, and they're going to provide the actual functionality. So by depending on abstractions, we actually add a layer of separation here, a layer of decoupling between high level modules and lower level modules. And this means that now we can swap out the data store here without any problems. We can switch from a concrete instance of file store to a concrete instance of HTTP store without having to change any of our code in data display. we see that both the data display, the file store, and the HTTP store, they all depend on abstractions. They all depend on this data store interface. And the data store interface does not depend on details. Right? These details of the implementation here, the implementation details of file store, they depend on the interface data store. The dependency inversion principle is, for me, one of the most useful principles, and I find this, when combined with other good practices of software development, to really bring our code, they all bring our code to a much higher standard in terms of understanding the code, so understandability, maintainability, and extensibility. So I find that the combination of these principles we have discussed over the last couple of sections are essential if we want to design great software.